Okay, let's look at the section 5.2, continued. I would like to go over another example of proof by contradiction, right? So here's the statement. We want to prove that the square root of 2 is irrational, right? So let's prove. So this is going to be proof by contradiction, right? So this is the lazy mathematician's notation for contradiction, right? So start with opposite of what we want to say. So we assume that square root of 2 is rational, right? So that's our given. Right? See if we can get some kind of contradiction, right? So by the definition of rational number, we know that there exists some integer, say m and n, right, such that square root of 2 can be written as a fraction of m, so m over n, right? And of course, since n is a denominator, n is a non-zero number, non-zero integer, right? So this is just coming from the definition of rational number. All right, then we can make a further assumption that all right, m over n is reduced. So that's another way of saying greatest we can assume, so we may assume that the greatest common divisor of m and n is equal to 1, right? And so this is without loss of generality, right? Because if the greatest common divisor of the numerator and the denominator is bigger than 1, we can simply divide a numerator and a denominator by that number. Then we can reduce it even further. So we just assume that m over n is a fraction reduced all the way, all right? So we can assume that. All right, then we have to do a little bit of algebra. So line 4, right? So we have square root of 2 equals m over n. Square root of 2 is hard to deal with. I'm going to square both sides. So which means that the 2 is going to be equal to m squared over n squared, right? And I don't like fractions, so I'm going to just multiply both sides by n squared, so that you can get that 2n squared is equal to m squared, right? So I don't have to deal with fractions, right? So this is just coming from line number 2 and a little bit of algebra there, right? But from here, you can see that the m squared is a multiple of 2, right? So you have 5. We know that 2 divides m squared, right? Then remember we actually showed this a while ago, the lemma that if 2 divides n squared, then it implies that the 2 actually divide n itself, right? So this implies that 2 divides n itself, m itself. So this is by lemma, so I'm using line 4 and also lemma. Right? Right, since 2 is, m is an even number now, so we have 6, right, by definition. There exists some integer k. such that the m can be written as 2 times k, right? So this is just a definition of even numbers, right? Or divisible by 2. All right, so I'm going to substitute 2k for m up here. So you will have line number 7, right? So 2n squared is equal to, right, m squared. So that's the same thing as 2k squared, which is 4k squared. Right, divide both sides by 2. We get n squared is equal to 2k squared, right? So this is just using line number 4 and line number 6, and algebra will get you that result. All right, but this indicates that n squared has factor 2, so it's divisible by 2. So 8. This implies that 2 divides n squared, so from line number 7. But we can again use the same lemma to conclude that it's actually 2 divides n as well, right? Then we have this contradiction, right? So therefore, right, if you look at the line 5 and also line 8, it tells you that m is divisible by 2 and n is divisible by 2 at the same time, which means that the greatest common divisor of m and n is at least 2, which contradicts the fact that we made sure that the greatest common divisor of m and n is 1. So this contradicts line number 3, right? So we get to the contradiction. So that's the end of our proof, right? So this will prove that since we assume that the square root of 2 is a rational number, then this actually got us in trouble. We got us a contradiction. Therefore, first assumption is false, which means that the square root of 2 is a rational number. All right, that's it. I hope that this was clear.